All right, so I'm Daniel Pelsmaker, and together with Hendrik van Antwerpen and my supervisors Casper Bak-Polsen and Ilko Visser, who is fortunately not here anymore, I present language-parametric static semantic code completion. So what is exactly the problem? How do we get code completion in our languages? We're writing these external DSLs, but we also have to expend additional effort to get editor features, editor services such as code completion. And traditionally, even in good editors that have good support for languages such as Java, the code completion you get is not semantically sound. That means it's not only suggesting things that make sense according to the static semantic rules of the language. One extreme example is Notepad++, where you basically get any name that you end up writing in your file, suggested as a code completion. But even in this example of IntelliJ, you see the suggestion for D, which is actually not in scope, where you invoke code completion, and the suggestion for the keyword null, which would not be valid as a return value for this function that returns int. So our contribution is a static semantic code completion editor service that is sound and complete by construction, language parametric. It proposes both syntax and references, and it is based on the static specification of the static semantics of the language. And with sound, I mean in this case that it only proposes completions that make sense within the static semantics of the language at the position where you invoke code completion. And with complete, I mean that it will suggest basically anything you could write there, both syntax and identifiers, modulo the names of declarations that you have not defined yet, and string literals or integer literals like this. So I will quickly show how static semantic code completion will actually look like. So imagine this program. This is a very verbose factorial function, and it has some placeholders in here. So this is actually an incomplete program, and we represent the incompleteness with placeholders, so basically holes. And we have two placeholders here, one for the declaration, the next declaration in the let expression, and another for the expression body of the let. Let's invoke code completion on the declaration. So we invoke code completion, control space in your editor, and you get a list of suggestions. In this case, the list of suggestions includes all the syntax that you could type here in this let expression. So this is actually the Tiger language, and it supports type alias, function declarations, variable declarations. And you can either omit or include the type. And you can see that these suggestions also include, again, placeholders for the various parts of the syntax. Let's say we insert a variable declaration. The variable declaration is inserted just like it was shown in the code completion dialog. And again, you get the placeholders for the different parts of the variable declaration. Well, we need to figure out an identifier for our declaration, but our code completion will not suggest a new name for anything. So we'll just name this one R. Now we can do code completion on the type of the expression. It will suggest basically all the types that you could put here. And since this is very unconstrained, you can write int or string or an array of these types, or even a placeholder for a type whose name you don't know yet. But we will see, if I first perform code completion on the expression, that actually code completion later on this type placeholder will have a much reduced list. So instead, I will perform code completion on the expression placeholder. And again, this is very unconstrained. It can be the first proposal is the method, the function reference, the factorial function reference, and the second one is a call to the factorial function. And basically, the next suggestions are more variants of all the syntax that you can put there. Let's put a call to the factorial function there. We'll insert it, and we end up with a placeholder for the argument to the factorial function. As you can see, the argument should be an integer. So if you perform code completion on this expression, we only get suggestions that could result somehow in an integer value. So of course, a call to the factorial function itself, or some of the other syntactic expressions, but notably array creation expressions or object creation expressions are absent. In this case, I just want to insert an integer literal. So actually, I will select integer const. You don't necessarily have to do this, but it's great for exploring a language and figuring out what kind of things you can put in the different places in your syntax. And since it's not suggesting any constants, because it would not make sense to make a list of all integers, we'll just write 5. If I now go back to the type placeholder and I perform code completion, you'll see that the list is much reduced. It's basically, it has to be int. Or if you can ever define a type alias for int, it could be any name that you could find right there. So it also suggests a placeholder for an identifier. We will use int here. And finally, we want to perform code completion on the expression body of the let, where it actually suggests not only the factorial function, but also the R variable that we just introduced. So we'll select that one and we'll insert it. So to show how we implemented this, I will first talk a little bit about Statix. As our approach uses the Statix specification of your domain-specific programming language. So you will have to define your programming language, static semantic rules, in the Statix specification, and then together with the code of your program, it will be run by the Statix solver, which will actually run on the constraints and produce analysis results. We'll go through a quick example. So the program on the left and then the highlighted expression hello plus a is represented by the AST on the right. And this is the syntax that belongs to that. So it's an add expression with 2 expressions on either side, a string literal, and then an injection. So an expression can be an L value, where an L value can be a variable with a given name. And this is the first Statix rule we're going to look at. A Statix predicate, type of exp, defines the relation between the expression and the actual semantics, in this case, the type. And the rule, type of exp for add, specifies the constraints that this expression must satisfy to satisfy the static semantics of the language. So in this case, it is an add expression of type int only if both sub-expressions are also of type int. The next rule we're going to look at is string literal, which is basically of type string. And a rule for the L value to expression injection, which just states that whatever type this expression is the type of whatever the L value is. And then a predicate for the L value, where the rule shows that if you have a variable of some name x, it will look up this variable in the context of a program and figure out its type. Actually, in Statix, it could return more than this. That's where the underscores come in, but for this example, I will keep it simple. So the way Statix solves these constraints is by starting with a constraint on the whole program, or in this case, our sub-expression. The type of this expression, and then the AST, has to be of some type T that's, as of now, unspecified. And by applying the first rule, we'll see that the type should be integer. However, it should also satisfy the constraints on its sub-expressions. So the type of the first expression, which is actually a string literal, should be an integer, and the type of the second expression, which is the L value injection, should be an integer. Expanding the first one again, we'll see that, of course, this will not make sense. An integer is not a string, so this constraint fails. And that's how the constraint solver figures out where the errors are in the program. The next constraint expands into the type of L value of a variable, which has, again, to be of type int, which expands into a query in the scope graph of the program, which looks up the variable a and finds the corresponding type, which in this case is int, so that's fine. So this is Statix in a nutshell, and Statix is not our contribution, but we are using its specification to implement static semantic code completion. So instead of having the Statix specification and the code just produce analysis results, we will continuously invoke the Statix solver to actually try a lot of alternatives and figure out what proposals we can actually propose to the user, which proposals actually make sense within the semantics of the program. We'll derive these proposals from the Statix specification and thus use the solver to filter them. So let's have a look at this example, again in Tiger, where we're trying to perform code completion on the expression in the function body. The statics rules are on the left and the syntax rules on the right. And again, note that there's an injection, exp to L value, which becomes more important later. So the first step in our algorithm is to perform an initial analysis. We have this incomplete program. It has a placeholder for some expression, but it's not specified. And therefore, the constraint solver, the normal one from Statix, will actually have some leftover constraints. There's a constraint on this expression that says that it has to be of type int, but it's not specified what this expression is, so this constraint cannot be solved. And that's actually our starting point. So we'll take this constraint, type of exp, and try to find all the alternatives that it could expand to. So in this small example in Statix, it could expand to add, new array, or L value to exp, which are the three alternatives we'll check next. So this second step is called expand predicates, and we'll now try to see which of these alternatives are actually valid within the static semantics of the program. So we'll run each of these alternatives back into the solver, and we'll end up with it will expand these constraints, and we'll end up with some constraints that fail and some that succeeds. And if any of them fail, those proposals are rejected. So in this case, the add rule will expand into its subrules that the left and right has to be int. The new array will expand into type of type, and the L value to exp rule will expand into type of L value, which is shown here. Well, immediately you can see that for the second case, new array, we have constraint that says that the type of this expression has to be both integer from the context and array from the rule. And of course, this one will fail. The other two are still fine, so we'll continue with those. Now, we could do more expansion here and expand again these type of exp rules, but we might do this recursively forever and just end up with something like expression plus expression plus expression, etc. And that doesn't really make sense. So we'll stop with the expansion after one step, and we could propose these proposals as code completion proposals now. However, the second one, L value to exp, is not that useful. It basically proposes another placeholder, but instead of an expression, for an L value. But if we look at the statics rules on the left, we can see that there's basically one alternative for an L value, which is a variable. So it would make much more sense to propose that one. So the third step actually, is to expand injections. So if we have an injection like this, like L value to expression, we expand it again, and we obtain the proposal for a variable with some name, which is again unspecified, and the type integer. Running the constraint solver again, it will expand this rule into a query constraint. The query says that the type of some variable with some unknown name has to be of type int. Well, we don't know the name, so the query constraint solver stops here. However, our fourth step is to expand these queries, basically finding all the names that they could resolve to in the program. So there's the n argument in the factorial function, and of course a reference to the function itself. We will now run all these alternatives again through the constraint solver, and it will reject the factorial function because that's actually a function type of int to int and not just integer. And these are then finally the alternatives that we have ended up with in this small example. The final step is to actually pretty print each of these alternatives. So the add rule, the L value to expression, and the variable n. And we end up with these three alternatives that we will propose to the user. And by construction, we know that these are sound. Every time we invoke the solver, it rejected anything that would not satisfy the static semantics of the program. So the only constraints, the only alternatives left are those that do. And we also know they are complete because of how we expanded from the initial rule, the predicates, the injections, and eventually the query constraints. So these are basically all the names you could find in the program that satisfy this, and all the expressions. of course, there are placeholders, so it's complete up to these placeholders. So these are the alternatives we would propose. And so this shows how we have implemented language-parametric static semantic code completion that is sound and complete by construction. It uses a static specification for your language that you implement in SpoofX. It's available in SpoofX. So SpoofX is a language workbench that we develop in Delft. It consists of multiple meta-languages, including Statix, which allow you to find the static semantics and also the syntax of your language. We've tested this on Tiger and ChocoPie. And if you want more details, please find them in the paper. Thank you.
Thanks. Thanks for the talk, Daniel. I have a question, like, is that approach limited to structural editing? Because like from the slides in the presentation, it looked very much like a structural editing.
Yes, currently it is limited to this kind of structural editing where you have these placeholders, but that is more a limitation of the environment in SpoofX in which we implemented it than a limitation of our approach. So in the future, we would like to have it such that you don't see these placeholders at all, that you just have an incomplete program, and that it would somehow infer the placeholders as soon as you invoke code completion, and that these are transparent to you.
Okay. And a second one, did you consider any kind of like ranking and between the available options where you can have an advantage with your approach over, let's say, other ranking approaches?
Yeah, so we considered ranking, but also it felt like a very complex problem out of the scope of our current approach. So we based our ranking simply on the fact that some alternatives have less placeholders, and those we'll put at the top, usually names. So those are probably the ones you want to have first. But there are many approaches to ranking, including machine learning to find the identifiers that are closest or most used. And we think this is great for future work.
Thank you.
So I have two questions. So in this slide, you mentioned you also tested on some maybe large language like Tiger, but I have no idea what that language is actually doing. But I'm curious, is it possible you can scale this approach to, let's say, the real languages? Let's say in the end, you can build a Java code completion tool based on this kind of static semantic analysis.
Technically, yes, you could scale this to larger languages. We chose these languages for our evaluation because these were the ones for which we actually have a static specification in SpoofX. Nowadays, we also have one for Java. So yes, we could scale this to Java as long as you have a static specification for your language in SpoofX.
So I think this means, because I'm a little bit confused, like you mentioned the statics. So this is actually not your contribution?
No, Statix is not my contribution.
Okay, so it's a kind of tool you use to let you describe let's say, some of the typing rules or semantic rules that you can use their solver to infer the possible candidates, things
Correct.
like that.
Yes.
So I think in that case, it seems that the problem would be how we can describe, the typing rules or even other semantic rule of a certain language in order to apply your approach. So do you think it is also possible that because we have compilers can do type checking very well, right? Because that's the only way to do the official type checking. So do you think it's possible that this kind of code completion approach should be embedded into the compiler, like you reuse their typing rules or their type checking algorithms, so that you can you don't have to, for each language you specify all the rules in a different meta language, things like that.
I see what you mean. I guess if you have some way to extract the typing rules such that our algorithm can find all the alternatives and try them, and a way to invoke the compiler to actually reject them if they're unsound, then I think, yes, you could use it with another compiler. But specifically, we used Statix because as part of the SpoofX language workbench, lots of DSLs are being written in SpoofX, and then it would be really great to have your code completion basically language parametrically without any cost.
If I may shortly react to the previous speaker, you claimed that compilers are very good at doing type checking, and those should be the sources of truth. If I'm honest, I would disagree, because type checker implementations in compilers tend to be very difficult and very hard to understand. And actually, the purpose of Statix as a specification language is give a more high-level description of type checkers that is easy to understand and reason about, from which we can generate such type checkers, so we can integrate them in compilers, but can also do other services like the ones presented. So therefore, I would suggest, well, considering taking these more high-level approaches, because they allow you to piggyback on the developments in the meta environment.
So I think if I get the idea right, so if you would make any changes to existing code instead of writing like new code, then basically your tool couldn't really recommend anything, right? Like if it breaks the code sort of in the process, sort of as soon as sort of, did I get the right? So there is nothing sound anymore if like the existing code already is sort of broken in.
Oh, you mean what happens if the existing code is unsound or has an error?
Basically, like that might happen if you, let's say you modify an existing program in some spot, like you may want to make a change and it's like in multiple places, and sort of while you're applying that, I guess your tool would kind of just not really be able to do anything in that point, or is that something you can actually handle already?
So there are two things here. One is if you have existing errors, of course, running the constraint solver again would resurface those errors. However, we will track them and not include them in the fact that these errors were there. So the proposals that still have these errors are not necessarily rejected. So if you have an error somewhere else in your program. And the second part is that, of course, if you have some semantic error in your program, it might actually limit indeed the possibilities that code completion could suggest. Say if it has to satisfy constraints that it could never satisfy, and yes, then in that case it would suggest way less.
Okay, thanks. Like it's great that it's not just I expected it to be like the answer is like nothing is possible at that point anymore, but it's cool that you can actually do something at that point. Thanks.
Hi. So you don't fully expand every possible path to generate completions before you show them to the user. Wouldn't you then encounter a situation, for example, with the like completion for accessing an object property, so like a.b?
Yes.
Where you want to have an integer in the end, but there's also no object in scope which has an integer field. But you would still suggest the completion for accessing an object property, even though it's actually impossible to fill that completion.
Well, correct. So it's a good question. If at first you get by default the suggestion for the syntax for a member of an object. So, for example, you would get something like exp or expression dot member name or something. That would be one of the suggestions, showing that actually this is a syntactic thing you could do. However, of course, you could argue that's not super useful because they're actually, you know what is in scope. You could actually suggest these names. So what you can do is augment your static specification with additional rules that make it such that the code completion will also expand into these kind of, say, member access. And in that case, it would actually suggest also the names of objects that have members or even members themselves. So you can tweak the specification a bit to get more useful code completion results. However, this does not affect the completeness.
Okay, thank you.
Hi, really nice work. It got me wondering about what would happen in a language that had parametric polymorphism with sort of implicit type application, right? So you have like f of type for all A, blah, 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 and you would need to instantiate A. So the declarative typing rules for such a thing would be non-deterministic. There are there are more algorithmic rules that are very complex. So I wonder, if you've worked in a language with parametric polymorphism in any of your examples, and if not, how do you handle non-determinism in typing rules?
Right. So we've not worked with parametric polymorphism. At least I have not in Statix. I think you can express some of it in Statix. I guess if you can express it in Statix, then it would work as you expect. And Statix solves their constraints non-deterministically. So usually it eventually ends up with an answer.
Okay. Yeah, I'd be interested in exploring that idea.
Yes, thank you.
Was it polymorphism?
Okay.
Thank you. Interesting talk. Well, it's related to his first question. So I wonder the applicability of your approach, because at the beginning you said it would be difficult. Well, you can apply this technique to, well, no, sorry. So existing Java editors cannot provide this kind of nice code completion. But on the other hand, if you also said that if you have the static specification of Java, you can do that. So I wonder why existing system IDE doesn't really provide this kind of thing, because as I said, you also said, well, compiler doesn't give a very nice type inference, but it would be possible to extract that part of a type system for the editors. So can you re-summarize? So what is the limitation of your approach, and what is the degree of the applicability of the approach if we can spend a lot of efforts to implement for more practical, mainstream languages?
Right. So I think it's very powerful that you know that all the completions you get are sound and complete. However, in practice, I've noticed that lots of developers don't really care that much about it. And
you mean the language designers or language implementers?
Users. So when you're programming, you often just use code completion to figure out all the names, and then you're basically iteratively thinking like, oh, this name, then this call, then this chain. And this way of thinking, well, it works somewhat in here because we have these placeholders. But in the normal editor where you don't have them, if it was complete and sound, it would not suggest any of those because they probably won't return the right type. And that makes it less useful for many users. And on the other hand, I think there's also performance. If you have a really large program and it tries to find all the possible identifiers that it could access, then it would be really
So do you say the key idea of this approach is the use of a structural editor in a certain sense? You mean because you repeatedly say placeholders.
Yes,
So
I say placeholders because that's how
it's a
I
structural editor, right?
it. Yeah, it's a kind of structural editor, I think. Yeah, so thanks to the placeholders in SpoofX, the editing looks a bit more structural, but it is actually still a textual editor, and it has still the benefits of textual editor. But specifically for our code completion, the placeholders are also for guiding and knowing where you can invoke code completion.
Yeah, I like that approach, but I just want to make sure what's the key idea. So that's fine. Thank you.
All right.
Okay, let's thank the speaker one more time and then lunch.
Thank you.